Alright everybody, welcome back. And by the way, Merry Christmas. This is the Will's Arcade Christmas Special. I've been working on this video for a bit, and it's still not perfect, but I wanted to give it a shot at least. Alright? Just a disclosure. This is the most basic information about this that I can possibly give you. This video is going to be fairly long, and it's probably going to be kind of boring for a lot of people. So I'm going to give you that heads up right now. But on this Christmas special, we're going to be talking about logic probes and integrated circuit gates. Okay, so all those little ICs and stuff you see on your circuit board, those are integrated circuits, and they have different types of gates depending on the type of IC that they are. Okay, and there are a few ways we can actually test those ICs, and the one way we can do that is part of this video: logic probes. Now, there are multiple different types of logic probes out there. I have two types currently. One of them is this HP logic probe. The code on this one states HP H05-10525T logic probe. Okay? This one is actually my favorite logic probe that I have. Even though it does not produce sound. You heard that right. There are logic probes that produce sound. This one, where this white band is, has light inside of it that basically shows the types of pulses and such going in and out of IC circuits. The second type of probe I currently have is this basic Radio Shack probe. Now, this is an old school probe, just like this one. They're both actually very old probes, and I'm not going to lie to you. Personally, the older probes are better than the modern day probes, okay? Again, they didn't build them like they used to, and the same goes with electronics, okay? But anyway, this Radio Shack probe is the same as this probe, except for a few things. One, it does have sound, so you can actually hear the sound frequencies based on the inputs and outputs of the logics that you're testing on a certain IC. The other thing is, this probe from the Radio Shack one is adjustable, unlike this HP probe. What I mean by that is, let's take a closer look. You'll see it has a high, a low, and a pulse. And then we have a couple switches. We have a pulse normal switch. Then we have a CMOS and TTL switch. Let's start with the top here. We have a pulse or a normal. Pulse basically represents the idea that most logics inside of a circuit board are not going to be a solid 1 or a 0 or a high or a low. They're going to be rapidly pulsing between high and low. Depends on the circuitry you're testing and what's coming through, because let's be honest, when we're talking about computers with the ones and the zeros and everything else, it's not just happening at a very small frame rate. It's going to happen rapidly, and that's known as a pulse. Basically on off at a rapid rate. Okay, you can change it to normal, which will prevent the pulse from activating, and you only have the high or the low. But anyway, now that you know the two probes that we're going to be using in this video, which again, it's a basic video, so there are other types of probes that we're not talking about. Go ahead and Google logic probes, and you will see what I'm talking about, that there are multiple different types of logic probes out there. Alright? And again, this is basic. We're not going into the extreme levels, alright? So, let me get you set up, and I can start explaining to you about the different types of gates you might encounter when it comes to logic testing, alright? Okay, so now that we've gone through the basic intro on the two types of probes that I personally own, we're going to go ahead and start talking about the different types of gates you can come across when it talks about working on ICs, okay? The very first one we're going to talk about is your most basic one of all. It's known as a buffer gate, alright? Try your best to ignore this part and this part, alright? We're going to start with the symbol. This is the symbol for a buffer gate. It's basically an input line to a triangle to an output line, which is represented as A being our input and B being our output. Now a buffer is basically just a straight through. So if you have a 1 or a 0 on A, you're going to have a 1 or a 0 on B. Alright? Now, just as a side note, with circuit boards running, like actively running the program and stuff, you're not going to normally get like a high or a low on the A, or the input. You're going to get a pulse or a toggle. Basically, the light on your probe is going to be bouncing between high and low, because it's constantly communicating with that IC. Now what that means is your B, or your output, should also be technically toggling or adjusting between a high and a low. Alright? Now what we're talking about is you're going to take your probe, and if you were to touch the input of this, and the light here is flashing, right? It's rapidly flashing. And then we come over to B, and it's rapidly flashing. Then that means this buffer is technically working the way it should. I mean technically, and I'll explain that later in the video, what I mean by that, okay? So, let's just go basic. Let's say you put it on the A, and you get a high input, or a 1. So the light on here is going to be solid. That means B is also going to be solid. And the same goes in reverse. If you have a low input, where it's a dim light, then the output is going to be also a dim light. Now, you can also have no light, which is basically like, it's like a locked in signal or a stuck signal. It's stuck high, stuck low, or it's open, meaning there's no signal coming whatsoever. So if you get like a stuck here and a stuck here, you might be good. It just depends on what's happening in the circuit prior to this IC chip. If you get a stuck high and then a stuck low, then you may have a problem with this gate, alright? Now, looking at the rest of the page, this right here would be considered what you call a truth table, alright? So you have your input and your output. So if you have an input of 1 or a high, you should have an output of 1 or a high as well. The same goes in the opposite. If you have a low output, you should have a low, or a low input, you should have a low output. Alright, so that's the basic truth table. Now remember, it's going to be toggling. Especially if the whole thing is running, it should be flashing on and off, on and off. And this output should also be flashing on and off, on and off. Alright? Coming over to this side of the page, this is a basic setup for what a buffer IC would be. Now this is a representation of a 14-pin IC. Pin number 1, which you can see the little notch I made right here, is the top left corner. That's pin 1. And they can be opposite, but pin 1 is typically your VCC, which is your voltage input to the chip. Pin number 8 on the bottom right is typically your ground. Now, these can be flipped around. Pin 1 can also be your ground, and pin 8 can also be your VCC or your voltage input. It just depends. The only way to truly find out is to look at a data sheet to see how the specific IC you're looking up is actually operated. Alright? But, basing it off this simple diagram I've made, let's say we look at pin number 2, and let's say it's flashing on us, right? So technically speaking, when we come through this buffer, pin number 14 should also be flashing. And that'll tell us that the gate is working properly. Alright? So that's the basics of a buffer. Now you might be wondering, why? Why do we use a buffer IC? Well, the basic answer to that is signal amplification. So what's happening when you use a buffer is you're taking a weak input signal and you're amplifying it to a much higher output signal so that you have the current capacity needed to drive the load that is needed for a specific circuit, whether it's going into another IC or say it's going into like a transistor or something. So if you don't have a high enough signal or a strong enough signal coming in to operate said IC or transistor, this buffer is going to slightly amplify it so the output can actually operate that load. Okay? Again, that's the most basic idea behind it. We can go more detail in a whole nother video, but this is the basics behind it. So let's go into the next IC gate and take it from there. Okay, so the next IC gate we're going to talk about is known as the NOT gate. Okay? Now, it's basically the same as a buffer, except for it's inverted. Okay? So when we look at the symbol here, you can see it's the same thing. It has an input, which is A, and an output, which is B, with the same triangle, right? But here's the difference. There's this bubble on the end. And that means it's inverted, which means it's opposite. So let's say, for simplicity, A is 1 or high. So it's going to invert that signal because of that bubble, and the B output is going to be low or 0. Alright? So, our truth table kind of shows that. If we have a high input, we have a low output. If we have a low input, we have a high output. Alright? Same concept. Here is a very rudimentary draft of how this works. Okay? So, let's say pin number 2, we're touching this with our probe, and all of a sudden, we got a high, right? When we come out to pin 14, we should have a low output. And again, like I mentioned before, it should be toggling if all the actions on the PCB board are working properly. So it should be toggle to toggle. Alright? But if you happen to have one that's stuck high, this should be stuck low technically. And that means that this gate in this IC chip is working properly. Okay? Now again, like we talked about before, with the buffer gate, why is a NOT gate used? It's basically exactly the same as a buffer gate, alright? Except for inverted. So, we're amplifying our input for a better output to drive a certain type of circuit, alright? It's just inverted. That's all it basically is. And I know that seems like a cop-out. It's super simple. And it shouldn't be the reason. And there is more detail to this. and we'll explain it in another video. Like I mentioned, this is all basic. So, it's amplifying our circuitry, but it's just doing the opposite of what the input is. And there's multitudes of reasons why that could be happening, okay? It all really depends on the design and the way the layout was made for the specific circuit it's supposed to be running, alright? So, now we kind of have the idea on the NOT gate. Let's move to the next one. Alright, so before we move on to our next gate that we're going to be talking about with IC circuits, I want to give a little side note when it comes to this buffer gate and the NOT gate. Now, the idea behind this, besides what I already told you about, signal amplification, you could actually, excuse me, you can probably see ICs similar to this in circuits that represent like push button actions. Like, say you have a button that, makes your character punch or jump or something, or if even your joystick, that's taking a 0 to a 1 or a 1 to a 0. And this might sound like a cop-out with this, but it all depends on the engineer who designed it, on how they want to do it. But basically, like, let's say you're playing like an arcade game or a crane machine or something like that, and you push the button to punch, or you push the button to jump, or you push left, right, up, or down with your joystick. Those signals are going to be traveling through a few other components before it gets to the IC chip, but ultimately these types of chips can be used for those, because you're just taking that signal, a 1 or a 0, and amplifying it and sending it essentially to the processing chip to tell the game's program what you want it to do. So those are some of the basic ideas on how you could use a buffer or a NOT gate, alright? Again, that's very basic. And again, it also depends on the designer of the PCB board on how they made all these actions happen. There could be multiple components before and after a specific IC that's a buffer or a NOT gate, and there could be other ICs after too that, transfer that data that's needed by the processor in order to tell the program ROMs what's happening, the actions and stuff. So I just wanted to make a quick little side note on that before we went on to the next gates, because these are the most simplistic gates you're going to find. They are, 100%. Not saying the other gates can't be used in those same types of circuits. Again, it all depends on how the designer or the engineer literally created the game and the board itself. So, let's move on to the next one, and we'll go on from there, guys, alright? Okay, so our next gate that we're going to be talking about is known as the OR gate. Alright? Now, if we look at the symbol here, you can see that it's kind of like a rounded triangle. So it's very similar to the buffer gate and the NOT gate, except for instead of being straight lines on our edges to a direct point, it's kind of rounded to a rounded little tip. Okay? And then also, if you notice, we don't have a straight line right here in the back. It's like a moon shape, like an inward concave kind of shape, alright? Now, you also notice something else compared to the other gates, the NOT gate and the buffer gate. The buffer and the NOT gate have singular inputs with singular outputs, which also, they can have more than one input and more than one output. Well, that's a much more complex kind of thing we can talk about in a more advanced video later on. The OR gates are always going to, bare minimum, come with 2 inputs with 1 output. And again, the same thing kind of applies here. You could have more than 1 input or more than 2 inputs with more than 1 output. But the essential idea besides a OR gate is what it says. It's OR. So, if you have a signal coming in on A or B, you're going to have a signal coming out on C. So at the truth table, that kind of shows us that idea. So if A has a 1, or a high signal, B has a 0, or a low signal, then the output is going to be a 1, because one or the other input has a signal. And as you can see here, if A is 0 and B is 1, C is going to be 1. So if we have A at 0, B at 0, then C will be 0. And the same goes if we have an A1 and a B1, we'll have a C1. Alright? So basically, like I showed before, we take our logic probe. If we touch the A input and we get a flashing or a toggle, which we should get with active circuitry, we should have a toggle on the C. Same goes if we have it on the B, we should also have it on the C. Now if you want to make it more simplistic, let's say A is high, C is going to be high. If B is high, C will be high. If A and B are both showing low, then C is going to also show low as well. And that's kind of shown in my rough, terrible diagram of an IC circuit here. Same thing as before, 14 pins. Pin 1 is our voltage, pin 8 is our ground. If we test pin number 2, and we get a high, or let's, in real terms, it's going to be toggling. If this is toggling, and then, of course, I brought this all the way down to 3, which does not happen in actual ICs. I'll show you when we get to data sheets. And that's toggling. Then pin number 14 is going to be toggling. So basically, if you get toggle on both inputs, you should have a toggle on the output. Alright? And again, a toggle is that light's going to be flashing. And if you're using the other type of probe that I have, the Radio Shack one that has sound, not only are you going to see flashing lights, but you're going to hear the actual data sounds, like the sounds of the circuit going on and off, high, low, 1, 0, 1, 0, so on and so forth. Alright? So, that's our OR gate. So, now we know how the OR gate works, let's figure out why we use the OR gate. Alright? Now, the OR gate is basically the same as a buffer or not. It's also amplifying our signals. Alright? So, no matter what, you're going to amplify the signal. But one of the biggest reasons why an OR gate is used is because of multiple inputs from multiple different sources. Essentially, this helps us compress the amount of ICs that we need for a specific circuit. And you're going to kind of see a theme here, that a lot of these different types of gates will help increase the amount of inputs and outputs by using even less ICs altogether. Ultimately, everything comes down to a point where you can make things happen by using less components and hardware. That's the biggest goal, is making things as small and compact as possible, and this type of gate helps with that. Alright, so now we know the basics on that. Let's move on to our next gate. Okay, so the next gate we're going to talk about is called a NOR gate, which is basically a NOT OR gate. Okay? As you can tell from the symbol, it's basically the exact same as an OR gate. We have our little crescent shaped backside with a rounded triangle. Okay? The things that change is that little bubble you see right there. That bubble means it's inverted. Alright? That's where we get the NOT from. What that means is the signals coming in, depending on our truth table, is going to be inverted on the output. Again, that's what the bubble means. It inverts it. So if you have a 1 coming through the output, that bubble is going to invert it to a 0. Alright? Now knowing that, we're going to go to our truth table. And as you can see, this is how the truth table works when it comes to a NOR gate. Again, a NOT OR gate. If A has a high and B has a low, our output is going to be low. While if A has a low and B has a 1, our output's going to be low. And the same goes for if A and B have a 1, our output is going to be a 0 or a low. The only way to get a high output from a NOR gate is to have both A and B have low inputs, or 0. Okay? So what that kind of means is if I take my logic probe and I probe the input A, if I have this bad boy as low, and then I probe B, and I have this bad boy as low as well, then we're going to have a high output on our C, which is a 1. Now, if A has a high output and B has a low output, we'll have a low on the C. And vice versa. If A has a low and B has a high, C will have a low. We need both of these to be low. Now again, like I mentioned before, I know I'm repeating myself. Active circuits, it should be toggling. Alright? Toggle, 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 and this should be toggle, toggle as well. Because again, it's rapidly changing data coming in versus data coming out. And there are exceptions to all these rules when it comes to like the toggle part. And we will explain that when it comes to showing you an active live PCB board. Alright? But what that basically means, if we look at our terrible drawing of a NOR gate here, if I look at pin 2 and 3, and both pins are toggling, right? That means pin 14 should also be toggling. And the same kind of goes with the effect of, if you have a stuck high and a stuck high, stuck low, stuck high, vice versa, this should be stuck low. If you have a stuck high, then this will be stuck low. If you have stuck low, then this will be stuck high. Alright? I know it sounds confusing, but that's just the basic idea behind it. Alright? So just think about that. Because again, an OR gate means either OR needs to have a signal coming in to have a signal coming out. But since it's inverted, if this one has a signal coming in and this one doesn't, then we have no signal out. Same with this. If this is an input and this doesn't have an input, this won't have an output. If they both have no inputs whatsoever, then this will have an output. Okay? That's the basic idea behind a NOR gate. So, as before, why do we even use a NOR gate? Well, a NOR gate is used as a cheaper, more efficient AND gate. The reason I say that is because the process involved in creating the IC chips that make a NOR gate is actually a lot more simple than it is to make an AND gate. So that's where it comes to be cheaper. Now, not only are we coming to the point of making it so that our gates can make us use less ICs and components to make the same kinds of actions happen, but now we're starting to talk about more efficient costs in order to make these same actions happen, okay? So basically, off what I'm saying there, it's more of a modern day version of an AND gate. They've amplified it and made it more efficient than the AND gate. AND gates are still really important in electronics, and they're still very useful. Again, those will all depend on who designed the game and the layout of the PCB and what it needs in order to make the certain actions happen. This is just a more cheaper, efficient version of the AND gate. You know, and again, they're both cheap. But when you're talking about manufacturing processes, when you're making thousands or tens of thousands of PCBs, every little penny obviously counts. So this is one of the ways they made it more efficient in the cost side to use NOR gates versus AND gates. So you can use a NOR gate in an AND gate circuit while saving a little bit of money if you're a main manufacturer, okay? So that's the very, very basics of the NOR gate. Let's move on to the next one. Okay, so our next gate that we're going to be talking about here is known as the AND gate. Alright? So, let's go ahead and look at the symbol. As you can see, it's basically the back part of the symbol is going to be a straight flat line. And then we have a rounded kind of like tip here, as you can see. Alright? We have two general inputs with one general output. And as said before, you can have multiple inputs, more than two, multiple outputs, more than the one. Alright, this is just basic. And the way an AND gate works is you need to have a signal happening on both inputs in order for the output to have the same kind of signal. Alright? So, looking at our truth table, if we have a 1 on A and a 0 on B, we're going to have a 0 on C. Alright? If we have a 0 on A and a 1 on B, we'll also have a 0 on C. The only way to get a high output is to have a 1 on A and a 1 on B, and that will create our 1 on C. So if you have a 0 and a 0 on A and B, you're also going to have a 0 on C. Again, and you have to have both inputs having some kind of signal coming in. So basically when you take your probe and you test A and you get a toggle, right? You know, it's flashing, or you have a solid 1 or something. And then you go to B and you have a toggle or a solid light or a 1. Then C is going to have a toggle or that solid light as well, okay? So if we have a 1 here, or we say A is flashing and B is stuck low, C is going to be low, or a 0, and vice versa, meaning B having a toggle, A having a stuck low, C is going to be 0. We need A and B to either be high or toggling. And again, when you're running an active circuit board, you should see a toggle because data is constantly going through 1s and 0s and so on. Alright, just like our truth table shows. Now when we look at my very rude drawing of a typical IC that has an AND gate, the same thing kind of applies. Alright, so let's say 2 and 3 are inputs and we have a toggle here and a toggle here. Our output on 14 should be toggling as long as this gate itself actually works, okay? So that's the basic idea of an AND gate. Pretty basic, pretty simple, right? But just like the others before, why? Why do we use AND gates? Well, basically, AND gates are primarily used with Schottky or Schottky transistors. What's a Schottky transistor or a Schottky transistor? Well, basically, a Schottky transistor prevents saturation of the stored base charge. So, essentially what I'm going on that, saturation is going to be like your depletion of a signal, so the weakening of a signal, and this can help prevent the weakening of a signal that's coming in. Alright? And that's pretty much what it is. I mean, that's what a Schottky transistor is. I mean, That's the primary use within this type of circuit, but you don't have to use it within a circuit that uses a Schottky transistor. Again, that's also extremely basic on a Schottky transistor. Excuse me. I'll make a whole nother video that has to do with different types of components like transistors, capacitors, diodes, etc. Okay? And that will go in a little more detail about a Schottky transistor. But typically speaking, when you have an AND gate IC, you're going to have some kind of a Schottky transistor or a Schottky diode that's within circuit to help prevent the weakening of the signals that are coming in and out of this specific circuit, okay? The idea behind this, if you think about it, when you look at the actual AND gate, so we'll go back to this here. Let's say you're playing a game that requires you to have two actions or two inputs to create a singular action. Like, let's say you need to use your joystick in a up and right motion, which would be at an angle, while including, say, a jump button. So your character, like, for example, in Tekken, would do a, not only like a front jump, but a front flipping jump. And that can be accomplished by using an AND gate transistor, because one of the inputs, say A, is going to be what your joystick is showing. So if you have an 8-way joystick, that can be put in the input of A, while the jump button, say button number 1 for example, and that's not true when it comes to like Tekken, but you know, if you had a game that used that, B would be the input of that push button. So combining the two at the same time would create the signal coming out to go towards not only the other components in line, but towards the processor that makes the game tell the actual programming that you are making not only a regular forward jump, for example, but it's a jump that has like a feature to it, like flipping or doing an attack or something like that. So you could use an AND gate for something of that nature. The other reasons why that we use an AND gate is basically it lessens the delay from the signals that are anticipated by the processor and the RAMs. So if you need a high-speed kind of logic switch between your processor and your RAMs and your ROMs, this would be the way you want to go, because it has almost no delay. Of course it has a delay, but the amount of the delay compared to other types of gates is so minimal that it allows rapid switchings to happen without causing your processor, your RAMs, or your ROMs to slow down or bog out on the information that they're taking in. So those are the basics on the AND gate, alright? Again, very basic. Not going into any more detail on that until we do a later video. So that's how you have to do that. Just remember that. You know, you need both gates, as the truth table shows, in order to get a high output. And also, like I mentioned before, it all depends on how the design was made by the engineer. Alright? Sometimes a 1-1-1 creates the opposite effect of a 0-0-0. So, if somebody programmed it so you have an action happen when both gates are high, so you have a high output, then that's one way that they made the design, versus the opposite, where if you have no inputs, you have an output of 0, which creates the action. But that can only happen depending on not only the processor, the ROMs, and the RAMs, but whatever components and ICs are before and after the specific IC running that gate, okay? I know it sounds kind of confusing. We can go into a lot more detail later on. I'm going to have to do my own research to be able to give you more details about it, because this video is all about the basics, alright? So now that we know the basics of an AND gate, let's move on to the next one. Okay, so the next gate we're going to take a look at is known as the NAND gate, or otherwise known as the NOT AND gate. And if you look at the actual symbol, it's the same thing as an AND gate, except for it has this inversion bubble right here. So basically what's happening at this point is it's going to be the exact opposite of an AND gate. Because if you remember an AND gate, you need a signal coming in on A and B in order for a signal to come out on C. But since it's inverted, if you have a signal coming in on A and a signal coming in on B, you'll have no signal coming out on C. So high is going to equal a low. This is going to be basically acting more like an OR gate. So if you have a signal on A, you're going to have an output. And if you have a signal on B, you're going to have an output. But the other key thing is, if you have no signal coming in on these inputs, you'll also have a high output, because it inverted it. You can see that in the truth table here. So, we have the low and low on A and B, we'll have a high on C. If we have a high on A and a low on B, we'll have a high on C. If we have a low on A and a high on B, we'll have a high on C. But if we have the high and high on A and B, then C is going to be low. Now, using this small drawing I have here of this, the same idea applies with all the others, with 14-pin sets, alright? So, if I probe pin 2 and then pin 3, I should have the inversion on pin 14. So for basics, if I have a high on A and a low on B, then I'll have a high on 14. And the same with vice versa. High on B, low on A, it'll be a high on C. And if we have a low, we'll have a high here. But if we have a high here and a high here, we're going to have a low on our output on 14. Now again, when a circuit's actively working, you're going to have these both toggling, which even means this pin 14 should also toggle, okay? Now, as you've already come to grow and learn, we need to figure out why. Well, the real reason why is the same as the NOR gate, alright? It's just another version chip that's more efficient to use in specific circuits that is determined on how the designer actually made the board, okay? The other reasons why mainly comes down to using these types of ICs in circuits that help give signals to a processor. It's kind of like the more advanced chip that helps with basic processing. So what happens is these chips are typically going to stay high or toggling high and things like that more often than none. And it's a sensory circuit that once the IC outputs a low signal, the processor in line is going to notice that low signal, and it's going to change various different pins outputs that go to other different types of things on the board. You know, whether it's a RAM or a ROM, or some kind of like a signal that's coming in from like the graphics or something like that. Again, it all depends on how they design the board, but it's kind of like one of those signals where it shows something needs to stay high, for example, and once it notices it goes low, then something else activates in the board. I guess a very basic way to look at it is almost like when you have a game running on the attract mode. They could be using a circuit like this to run high into the processor, and when you coin the game up, that circuit's going to go low, which is going to tell the processor the game has been booted up or coined up or started. Alright? So, again, you can use these in multiple different forms. It all depends on how they made the board and how they wanted it to work. But that's just kind of like a basic example or idea how you might be able to use this in a circuitry, or how they may even be using them in a circuitry. Alright? So let's move on to the last gate. And the last gate isn't really a basic gate. It's a more advanced gate, but it's kind of like a taste into what we're going to be talking about in a later video when we go into a little more detail on all the gates, including the one that's coming up right now. So we can call it like a bonus. Alright? So we'll be right back. Okay, so the final one we're going to discuss is called an XOR gate, or an exclusive OR gate, okay? Now, this is a much more advanced kind of a gate, and we're not going to talk too much about it. This is more like a quick little bonus, so I'm going to make it as quick as I can, because this needs a lot more description and understanding about how they work and what they're used for. But I can at least give you kind of a general idea about the basics on it, okay? Now, if you look at the symbol, it is the exact same as an OR gate, except for a couple little things. One being right behind this little moon-shaped curve, we have an additional moon-shaped little line right there. That line right there gives you the indicator that this is an exclusive OR gate. Alright? Now, technically speaking, I have A and B on my inputs, which is correct. I put C on the output just to kind of make it more understandable from the previous gates we talked about. But when you look up data sheets and such, the output on here is going to actually be labeled as Q. Alright? One of the reasons why is a lot of these types of gates are going to be used in timing circuits or clocking circuits, or within the circuit that helps make the processor understand certain types of needs and wants from other parts of the circuit board. Alright? This is why I'm saying this is a much more detailed part, so we can talk about that later. And besides there being exclusive OR gates, there's also exclusive AND gates, exclusive NOT gates, etc. So we'll talk about them in a later video when we kind of dive deeper into it. But if we look at the truth table for this, it's almost exactly like an OR gate, alright, where you see 0, 0, or low, low, is going to create a low output. And then you have a low A and a high B will create a high output, while a high A and a low B will also create a high output. But, unlike the OR gate, when in an OR gate, if you have A and B both high, you'll have a high output. But because this is an exclusive OR gate, if you have a high on both inputs, you'll have a low on the output. And that's where it comes to the point of the exclusive part. The exclusive part technically means that you can have either or for the inputs having a high signal, but you can never have both of them having a high signal at the same time. So, looking at my rudely drawn schematic of an IC for this, if you were to test pin 2 or pin 3, and you get, say, a high on 2 and a high on 3, then pin 4 is going to be low. But if you have a high on A and a low on B, pin 4 will be high, and vice versa, okay? Now, I know, why is it used? Now here's the thing, I'm only going to give you the most basic reason why. We have to go into a lot more detail. Even I have to do a lot more research to be able to give you a better answer. But the best answer I can tell you is a lot of these types of circuits that use exclusive ORs, exclusive ANDs, and so on are being used within a clocking circuit or a timing circuit or some other form of a circuit that goes to like a processor or a processing power kind of IC chip. Because what's happening here is the signals coming out of it are going into, say, your processor, right? Or even, you know, it'll still go into your processor if you're using it in a clocking circuit. Essentially what's happening, it's using these signals to count the ones or the high units that happen in a certain amount of time. And depending on how the program is written, those number of ones can be used to make certain actions happen. The reason why I say you can use it in a clocking circuit is, like, the most basic idea about a clocking circuit is it's going to send signals to the processor, and then after a certain amount of time or a certain amount of highs, like outputs for example, it will reset and start recounting. So pretty much like a processor or another circuit is looking for an X amount of high frequencies or ones in a certain amount of time. And as long as it reaches that certain set number, the circuit will reset the counting part to recount the same numbers. But if you don't get the numbers required, so let's say you require 20 ones in order to make the circuit continue to work, but you get 19 or 18 or so on, then all of a sudden the whole circuitry resets. Like, it can't tell what to do. So if you have a game that's resetting, like it starts up and then immediately turns off and turns back on, it's resetting. This could be part of your issue. You could have an exclusive OR or an exclusive AND or so on that's causing a problem in that circuit, so it's not outputting the required amount of high output signals needed by the processor in order to continue the game's functioning. And if it's able to do that, when it resets the count, it'll continue to work. But if you get less than what's required, it'll reset the game program. Alright? I know that seemed quite long for what I'd call a basic description, but that is basically the basic description. We'll go into a lot more advanced detail later on, okay? This is all about basic stuff. So, let's move on to the next part, and it'll keep this video going, alright? Okay, so we've learned about the majority of the basic circuits that, the gates that are going to be used in our circuits on our circuit boards themselves through the IC chips you're going to find. Now, again, the exclusive OR gate is not what we call a basic. Our basics are going to be our buffers, our NOTs, our ORs, our NORs, our ANDs, and our NANDs, okay? Those are the basics. This is a more advanced gate, alright? But I'm about to tell you something that's going to make you go, damn it, are you serious? And here's the deal. Even if you go through all these gates with your logic probe, and you have toggling inputs, toggling outputs, so on and so forth, where it appears these gates are working the way they're supposed to work, that doesn't mean they're actually working properly. All the logic probe is going to do is tell you that the gates are taking in the signals and outputting the signals the way the gates were designed to do so. Again, if you're talking about a buffer gate, if it's toggling in, it should be toggling out. Same when it comes to the NOT gates, the OR gates, and so on. So if you have toggle, basically a rapid 1 and 0, or there's action or activity of signals coming in of the gates, you should have the same kinds of outputs, okay? So if you have a toggle in, you should have a toggle out. Being stuck high and stuck low for an input or an output, that's going to determine and depend on what's happening in the game. Because there are going to be certain circuits where you're going to be testing it and you're like, oh my god, it's stuck high or it's stuck low or so on and so forth. And you're going to think that's a bad gate until you do something, like say coin the game up or start the game. Because if you coin up the game, all of a sudden certain circuits are going to toggle that weren't toggling before. And when you actually start the physical game, there'll be circuits that are toggling that weren't toggling before. But you could still have a game that's not working correctly if all these are still toggling when they're supposed to and how they're supposed to. The only way to find out if the circuit is truly bad, if you go through all of them, correct, and they're toggling like they're supposed to do and when they're supposed to do, is by using a device called an oscilloscope. Unfortunately, I don't have an oscilloscope currently. When I do finally get one, I will make a video on how to use an oscilloscope and the purpose of them. But the most basic idea about an oscilloscope is they are used to actually physically see the waveforms that are coming in and out of a gate circuitry, okay? So let's say we're talking about an AND gate and it's toggling perfect. Your logic gate is telling you like, okay, that gate is working. But you may have data that's either coming in or coming out of it that has been corrupted by some kind of damage within the IC chip. And the only way to really tell if that's happening is by using an oscilloscope and checking out the waveforms that are coming out. You can find a lot of the information on what the waveform is supposed to look like by looking up various different types of data sheets, okay? So that's kind of the most basic touching on that. So let's go get set up on our circuit board and we'll take it from there, guys. Okay guys, sorry that it's a little dark. I'm doing this so you can see some things a little bit better. Obviously you can't see the circuit board very well. You can kind of sort of see it. You can see the red light, so you know it's powered up. And of course it's a centipede. I have so many of these, I'm just going to use it as my test bench. I'm just doing this quick to show you. It is a working centipede. So what we're going to do is I'm going to show you how to hook the logic probe up to the circuit board. And then I'm going to show you some basic ideas on how to test the different logic gates. Now, of course, with this board working, as a side note, we're not going to really find too many problems. But I might be able to find some ICs in the circuit here that aren't toggling because it's in attract mode or doing something else, okay? So if I can find them, I'll definitely point them out to you. And if not, at least you get the idea about how to attach your probe and how to use it with a live circuit board, especially safely, because you don't want to fry the circuit board because you made a simple little mistake. Alright? So I'm going to get you all set up and we'll start doing the probing. Alright guys, so now it's time to start doing a little bit of probing, okay? Now, I'm going to tell you, out of all the logic probes I've had, I've never had one have high DC voltage inputs. I've always had ones that just use 5 volts, alright? I'm not saying that higher voltages like 12 volt ones or so on don't exist. I just don't see the purpose of it. But all the ones I've ever owned are 5 volt, alright? We're going to start with my HP probe first, okay? There it is, the HP probe. As you can see, we have a red and a black lead. Obviously the red is going to be our positive voltages and the black will be our ground. Now, what you need to know is you don't hook this probe up to your power supply. You need to hook it up to your ground and your voltage inputs on the circuit board. And there's a few ways you can do it, okay? I'm going to take you off the tripod for a second just to kind of give you a close-up here. We come down here, see if I can't get the view right, there we go. You can see there's a 5 volt test tab right there. Sorry for the focus, but there's your 5 volts, right? And then we come down here, we got our ground, GND, that's your ground, okay? So we could go ahead and put our negative or our ground right on the ground plane, and then put our positive right there on the positive 5 plane. But if you notice, that's a pretty big gap, alright? Some probes you can make that gap, others can't. Here's what I like to do when I'm in a situation like this, that is. This cap right here, this is your voltage filter cap for your 5 volt rail, alright? So, one side, as you can see right there, says positive. That means the other side is our negative. And if you don't trust that, you can take your multimeter and probe it out, and you'll find that this plane is your ground plane. Okay? So what I'm going to do is I'm going to put my positive lead right there on the positive leg of the capacitor, and then the negative lead's going to go on the negative side of the capacitor. And we're going to get 5 volts. And it'll be interactive with the circuit board. That's the most important part of this all. You need it to be interactive, or at least attached in the same voltage rail system that your circuit board's in. Now if I wanted to, I could also use that ground pin right there, you know, but it's still a decent sized gap. So there's no point in doing that, in my opinion. Let's just go ahead and stick with the basics here. So I'll put you back on the tripod. Okay, just like so. Now, like I said, you're going to take your positive lead and you're going to hook it up to your positive, alright? And the same goes with your negative. Now, as you can see with my probe, it's pretty old, and the positive here has lost most of its protection. So you want to be extra careful just to make sure that this is not shorting out against your ground plane or anything else on your circuit board. And the same goes with your negative gator clip, alright? Make sure it's not shorting out on anything. That's the big thing. Because if you do that, not only can you cause damage potentially to your circuit board, but your probe itself could also become damaged too. These things are really sensitive, so be careful about that, okay? So now that I've got that set up, what I'm going to do is I'm going to power the game up. Sorry about kicking the tripod, I didn't mean to do that. So here we go, we're going to power it up. And as you can see, my probe has just a solid, low dim kind of light. It's like more medium range. You'll see what I mean when I start probing some different things, okay? Just for a quick example, let's see here. This leg on this capacitor right here is a positive. See how it got brighter? I might have to zoom it in a little bit. Hang on, let me zoom you in. Sorry about that, guys. The batteries died in the camera, so I had to change them out real fast. But back to what we were talking about, okay? Now we zoom in, and you can see we got a positive right there on the cap. It might be hard to see, but when I touch this with the probe, okay, you can kind of see it. It's barely seeable on this camera, but it gets slightly brighter, okay? That's essentially your 1, or your high, right? Let's go to the negative side. See, it turns off. That you can definitely see. There's your 0. Now, there are going to be times where it's not going to turn off, and it'll just get a little dimmer than what you can see right there. And that's still going to kind of represent your low or your 0, okay? Now, since we're already kind of zoomed in and down here, let's take a look at some of these chips right by here, alright? So, let's see here. Oh, we'll look at this one right here. This one here is a SN74S74, alright? Pretty common IC. Alright? Now, if you look up here, you see this little U shape? That U shape or that notch, that's what I've been showing you on my horribly designed pictures I made, which represents where the number 1 pin is, which is right here. The one right next to it. You can't see it on the camera, but it's right there next to it. And then down here is going to be our ground. Oh, no it's not. Oh, this one. This pin here is the ground on this chip. Again, it helps when you look at a data sheet. It's going to show you all the info. See? Turns off. That's your ground. And this one should be your voltages. Yep, see how it goes high? That's your volts. Now, like the one pin I showed you, pin number 8. See it flashing? That's what I mean by toggle. Alright? That means there is signal coming in and out of this circuitry. Alright? And we can test all the others. You see we got a toggle. Oh, there's a high. There's a toggle, and a high. And another high. So, that doesn't mean that that chip is bad, okay? We're on a track mode, so that chip could be working with some kind of a circuit, like the video circuits or the sound circuits or something like that, that just hasn't activated those specific gates yet, okay? So, let's move on over here. There we go. Okay. Here's a ROM. This is an EEPROM. Okay? Same thing. It has a notch right up here. As you can see, silk screened on the board pretty well. There's your notch. So the pin right here is going to be our pin number 1. And it's toggling. Now, ROMs might be a little different on what ones are your voltages and your grounds, okay? Again, this is what a data sheet is for. See all that? Now, I can tell you right now that these two ROMs are graphic ROMs. So, since we have a title screen or a attract screen on, that's why these things are, for the most part, activating and are accurate. Because there's motion happening on the whole attract mode. Okay? See that? That's what I mean by toggle. You should have toggle when it comes to things being activated, because the processors and stuff, they're not always looking for a solid 1 or a solid 0. A lot of the times these circuitries are constantly going high and low because multiple things are happening. So you're going to see that toggle, meaning it's going high and it's going low multiple times, which is a good thing, okay? So that's one of the key things to just kind of remember, is not everything is going to always toggle. Sometimes you have to start the game, and you'll find that certain things toggling will stop toggling, or vice versa. And of course, you want to be careful when you do this, because if you're not careful, and say you go a little bit to the side, you may accidentally short out 2 of these pins. And that could cause damage. It's not guaranteed it's going to, but it could. Now, I'm trying to find some ICs or ROMs or something on here that I just don't want to activate because it's only in attract mode. Now, I'm not gonna lie, I don't know which ones off the top of my head is gonna activate and not activate and so on and so forth. So, let's see here. That went low. That's toggle. That's toggle. That's just stuck high. That's stuck high. Stuck high. And you see though? So you can also look right here where it says, let me give you a better angle of this. This is a good way to test some of this stuff too. You see some of these little test pins here will say like ROM 0, ROM 1, ROM 2, so on and so forth. These are the activation signals, the ones that activate the ROM specifically. If you were to touch them, you see how it's toggling? That's a good thing, because the ROMs are going to need to turn on and off rapidly, or this is actually the enable circuit. So they're enabling the way they're supposed to enable. Now down here, you see these kind of weird little symbols. These are actually your clocking circuits. So you can also test those too, and see if they're toggling, which they should be. They shouldn't be stuck high or stuck low. The same goes for up over here near the actual clocking circuit. You know, right here is a 12 megahertz. We got that. We got our 6 megahertz and our 4 hertz. So, you know, those are good things to have. Now what I'm going to do is I'm going to go ahead and coin the game up quick, and we'll go ahead and start it, and we'll see if any of these ROMs change, like the toggles, like the ones you notice that were stuck high or stuck low. And then if it does, then look at that, we found a circuit that actually is activated because the game has been activated, alright? And again, if I can't find any to show you, you'll get the idea when you actually start doing this yourself. I promise you, you'll start figuring out when you compare your circuit board to the data sheets that you're looking at for the specific ROMs or ICs that you're looking into. So let me get this coined up. We'll be right back, okay? Okay, so I got it coined up. Now we're going to go ahead and start it so you can hear the sound. Okay, so now let's see if any of these toggle. Okay, so it doesn't look like I'm going to be able to find you any of them that toggle when it's in game mode versus attract mode. But that's okay, because it's all about the idea of how this is done. Okay, so now you've seen one type of probe. Alright, that's the HP probe. Now I'm going to show you the Radio Shack probe I have, which, by the way, it gets hooked up the same way that my HP probe does. You have a positive and a negative cable, as you're about to see here. First, let me zoom you out. Okay, you're zoomed out. See? A positive and a negative. Now, the difference between this one is, it's got lights that indicate a high input, low outputs, and vice versa. Your pulses, and you can switch it between like pulse modes, transistor to transistor language, or CMOSes. But what the cool part about it is, it has a cheat sheet right on the back. It gives you the indicators and the ideas of what's supposed to be happening. The other cool part is it's got sound. So I'm going to hook this up the same exact way that I hooked up my other probe, and we'll do a little bit of testing. You can hear the sounds that it makes and the different types of inputs and outputs. Okay, so let's go back to our clocking circuit right here. Right, you hear that? That's a clocking circuit. Come over here. See? That's without the pulse switch being activated. See how the frequency is changing? The sound changes a bit. It's because it's various different types frequencies, which changes the sound, alright? Now if we go to, say, one of these ROMs here, or EPROMs, we got a high. See how it's high? Then we got pulse. Now, I'll show you what a low on this would look like. So let's move you over a little bit here. so you can see the groundings. Okay, so back to the same kind of capacitor idea. If I stick it on the positive, oh, they're not getting it this time. Oh, there we go. See the low? Let's find our 5-volt rail again. It's over here, I believe. Yep, right here is the 5-volt. See how it's stuck high there? With a little bit of pulsing in between? Oh, you can't even see it. I'm sorry, guys. Gotta zoom it out a little bit more. Okay. See that red light right there? It's stuck on high, because that's our 5-volt rail. Now, if we were to come over to our ground over here, and do the same thing, see, it's stuck on low now. So that's how you can use one of these to kind of test the same ideas between a high and a low. And we'll do the same with some of these ROMs over here, these EEPROMs. Stuck high, pulsing, pulsing. So when you look at one that's pulsing, right, or essentially a toggle like this one here, let me readjust you so you can see this better. Okay. So we'll find one that's toggling. There. Now you notice that the high and the low lights are on, and then the pulse light is on too. The reason being is both these lights are going to be on because this one is actually toggling. Like if you saw at the last probe, the light's flashing, which represents a toggle. Well, both lights are on because it's toggling. It's literally going back and forth between the high and low. And then that pulse light is what tells you that it's actually toggling. So, for example, if you had one of these where you had your high and your low on, but the pulse light wasn't on, then that means that it's actually not toggling, okay? You may have an issue there. And the same goes for any of these other types of circuits or ICs that you test with this. See, that's toggling, that's toggling, that's high, that's toggling, so on, okay? You can even do that down here where you have your vertical sync and your horizontal sync, alright? Let's see if I can't zoom you in just a little bit. Alright, it's not going to focus very well, but this right here is your vertical sync. Not only is it toggling, because you can hear that sound, right? Because it's switching so fast. Go to the horizontal sync, it's not switching as fast, but it's still switching and toggling, okay? So, yep, that is the basics on how to use and hook up a logic probe, okay? Of both types, at least that I own. I know this probably wasn't as informative as you may have hoped it would have been. I kind of feel like we could have gone into some more details, but I wanted to try to make this video as basic as we could, kind of like a 101 on probes, I guess you could say. So a lot of this is going to come down to you just doing practice, and then learning and understanding how to read data sheets. That's going to make things a lot easier for you. And as a little tip, I want to also say, if you're looking at a data sheet and you start testing that IC and you're like, wait a minute, this gate isn't working properly. Before you say that chip must be bad, one, go back in the schematics of the board and make sure that that gate is even being used for one. Two, make sure that the IC chips before that gate are also working properly. And three, make sure that you coin up and start your game. Because some chips are not going to be activating or toggling like they're supposed to if the game isn't actively being played. If it's only in tracked mode, you might not get every single gate in here actually working. So that's something to keep in mind. And like I mentioned a little bit ago, if you go through this entire board, coin it up, power it up, so on and so forth, and you have every single chip working the way it should work, then you need to go ahead and get your oscilloscope out and start making sure your waveforms are correct. And again, when I get an oscilloscope, we'll make a video all about those as well. Alright? But that's pretty much going to be it, guys. There's not much more I can really show you when it comes down to like the basics. I hope you learned a little something at least, or at least gave you an idea what to look into if there's more questions you may have. I can do my best to answer your questions, regarding these, but beyond this, I'm going to have to even do a little more research myself, so the more advanced video is going to take me a while to do. Other than that, thank you so much for watching. I appreciate it. I hope you guys have the best holiday season out there. And, actually the best New Year's you can possibly have. So, thank you again, guys. This was a wonderful year. And I can't wait to see what happens in 2023. Take care, and we'll see you next time.